Hello, this will be a demonstration of proposition 36 from book 3 of Euclid's Elements, which says that if a point be taken outside a circle and from it follow two straight lines, one cutting the circle and the other touching the circle, then the rectangle contained by the whole cutting straight line and the straight line intercepted between the point and the convex circumference will equal the square on the touching straight line. This looks like is that we are given a circle ABC and some point D outside of it, like so. We have two straight lines falling from this point onto the circle. One of the straight lines touching the circle. Just gotta make sure it actually touches it, so. And the other cutting it, like so. And what we must prove is that the rectangle contained by the whole of the cutting straight line, which is AD, and the straight line that Euclid says is intercepted between the point and the convex circumference, that here would be referring to the straight line DC, right? So we see it falls between the point and the convex circumference. The rectangle contained by the whole DA and its segment DC will equal the square on the touching straight line DB. Now, this cutting straight line, DCA, will either fall through the center of the circle ABC, or it will not fall through the center of the circle ABC. Now, if it does fall through the center of the circle ABC, let's begin by taking the center of the circle ABC. We'll call it the point F. We did this by proposition 3.1. And then we join the straight line FB. All right, that's postulate 1. Now, because the straight line DB touches the circle ABC at the point B, and a straight line has been joined from the point of contact to the center of the circle, we can say by proposition 3.18 that this angle here, FBD, is a right angle. Excuse me. Now, because AC has been bisected at the point F, right, so AC, which is the diameter of the circle, any diameter is bisected by the center, in this case point F. So AC is bisected at the point F, so AF equals FC. AC having been bisected at the point F, and the straight line CD being added to AC in a straight line, we can use proposition 2.6, which tells us that if a straight line be cut into equal segments or cut in half, and a straight line be added to it in a straight line, then the rectangle contained by the whole plus the added straight line and the added straight line plus the square on the half will equal the square on the half plus the added straight line. What that looks like here is saying that the rectangle contained by AD, which is the whole AC plus the added straight line CD, the rectangle contained by AD and the added straight line, namely DC, plus the square on the half, in this case FC, will equal the square on the half plus the added straight line. What that looks like in final force is that the rectangle AD times DC plus the square on FC will equal the square on FD. Right, so we have FC at the half, and then FD at the half plus the added straight line. And because FC is equal to FB, their radii are the same as circle, and so by definition 115, we know that they must be equal. We can substitute FC squared for FB squared, so we can say that the rectangle AD times DC plus FB squared will equal FD squared. Now, looking at what we have here, we actually have a right angled triangle, FBD. And using proposition 147, we can say that the square on FD will equal the square on FB plus the square on BD. So that FD subtends the right angle, and the remaining sides FB and BD contain the right angle. And so FB squared plus BD squared will equal FD squared. And having two things equal to the same thing, namely FD squared, we can say that these two things are equal to each other. And we can say the rectangle AD times DC plus FB squared will equal FB squared plus BD squared. Now you'll notice that we have the same thing on both sides. We have FB squared on both sides. So by common notion 3, if we subtract equals from equals, the remainders will be equal, so that we can say the rectangle AD times DC will equal DB squared. Now this is what we set out to prove, so we are done with this portion of the proposition. However, we assumed that the secant straight line, cutting straight line DCA, will fall through the center of the circle, but this is not necessarily the case. In fact, it's much more likely that we'll find that DCA does not, in fact, fall through the center. So let's deal with the scenario in which it doesn't. We'll have the secant straight line, DCA, fall onto the circle, ABC, not through the center. And we'll have DB, again, touching the circle at the point B. Now, if this is the case, we begin by, again, finding the center of the circle, ABC. We'll take that as point E. We do this by proposition 123. Next, we draw the straight line EF perpendicular to AC from the point E. This will be using proposition 112. So we will have EF, like so, perpendicular to AC. And finally, we shall have the straight lines EB, EC, and ED. We do this all by postulate 1. Right. Now, again, using proposition 318, because DB touches the circle, and from the point of tangency, a straight line EB has been drawn through the center, or to the center. We know that this angle here, EBD, must be a right angle. Now, EF being through the center, right, we said that the point E is the center, so EF is through the center. It's perpendicular to a straight line not through the center, namely AC. And so we know by proposition 3.3 that not only is EF perpendicular to AC, EF also bisects AC at the point F, so AF will equal AC. Now again, we have a straight line cut in half and a straight line added to it in a straight line. Again, this is AC bisected at the point F, and the straight line CD being added to it in a straight line. And so we can use proposition 2.6 again to tell us that the rectangle AD times DC plus the square on FC will equal the square on FD. Now we'll add the square on FE to both sides. We can easily do this by common notion 2. And so we can say that the rectangle AD times DC plus the square on FC plus the square on FE will equal the square on FD plus the square on EF. Now again, we have several right triangles going on here. We have the right triangle FEC and the right triangle FED. And using proposition 147, we know that ED squared will equal FE squared plus FD squared. And again, EC squared will equal EF squared plus FC squared, which means that in our original equation, which we came to by proposition 2.6, we can substitute FC squared plus FE squared for EC squared. And similarly, we can substitute FD squared plus EF squared for ED squared. So that we can say that the rectangle, the rectangle AD times DC plus EC squared will equal ED squared. Now, similar to the previous part of this proposition, we know that EC and EB must be equal. They are radii of the same circle, so definition 115 tells us that they're equal. And the squares on equal straight lines will also be equal. And so EC squared will also equal EB squared, which means that we can again substitute EC squared right here for EB squared and say that the rectangle AD times DC plus EB squared this time will equal ED squared. Now, using proposition 147 for a final time, we know that ED squared right here is in the right, But we have the right angle triangle EBD, which means that proposition 147 tells us that ED squared will equal EB squared plus DB squared. And we have two things equal to ED squared, so by common notion 1, these two things will be equal to each other. And we can say that the rectangle AD times DC plus EB squared will equal BD squared plus EB squared. Now we have the same thing on both sides, so by common notion 3, we can subtract this and the remainders will be equal. So that we can say at last that the rectangle AD times DC will equal DB squared. Now this being what we set out to prove, we are done with the proposition, therefore, etc. QED. Nothing to add to this proposition, so I will simply move on to proposition 337.